class, we have just looked at elements and we looked at isotopes. Now we want to study the periodic table. The periodic law and periodic table was conducted by Mendeleev. Mendeleev's idea was to arrange elements in order of increasing atomic mass. That was his idea why he decided to arrange elements. And when he was doing that, he observed some kind of a pattern, a repeating pattern of properties. So you can see. So with that, he decided to arrange them. Elements with the same property, he decided to put them in the same column. So this was his idea. See, we're just trying to arrange them according to their increasing atomic mass. Periodic law. When the elements are arranged in order of increasing atomic mass, certain sets of properties reoccur periodically. So he decided now to put the elements with similar properties in the same column. And what he noticed is that the elements with the same property fell in the same column. You can see. So he used pattern to predict properties of undiscovered elements. So after he has done this, he used this pattern now to try to discover elements which were not yet discovered. He just predicted what these elements which are not yet discovered, where they will be and how they will look like. So that is what happened. Germanium was not discovered. By the time that silicon was discovered and tin. So he came up with a proposal and predicted that germanium atomic mass will be 72 and it will be gray and its density will be about 5.5 and it will resist reacting with both acids. So he just proposed its formula with oxygen will look like this. Based on what he knew about silicon and tin. And when germanium was discovered, that was its average atomic mass as predicted. And its color was gray-white, close, almost the same. And its density, when it was discovered finally, was measured to be 5.4. And it was true, it resisted both acid and base. And this is its oxide, the formula of its oxide. So when you know the property of one element in a column, in a group, or its formula, you should be able to predict how the formula of the other element in that particular group is going to, in that particular group, yes, group or column will be. So modern periodic table, based on Mendeleev's landmark contribution, the modern periodic table was founded. And the elements were arranged according to their atomic number of protons, and not according to atomic mass, as Mendeleev did. So based on their properties, these elements were divided into three large families: metals, non-metals, and metalloids. So let's look at how they are arranged. So you see the metals have this color, you see, somehow close to yellow. Then the metalloids divide the metals from the non-metals. So metals are on the left of the periodic table and non-metals are on the right. In between them, like a staircase, you have what we call the metalloids. Please, you need to know this. You need to know this. So look at some metals and their properties. Metals are solid at room temperature except mercury. Reflective surface, it means they are shiny. They conduct heat and electricity. They are malleable, it means they can be shaped. They are ductile, it means you can draw them or pull them into wires. And generally, metals lost electrons in reaction to form cations. About 75% of elements in the periodic table are metals. You can see example here, this is copper. See. Lower left on the periodic table, they are on the lower left on the periodic table. Let's look at non-metals. Non-metals found in all three states: solid, liquid, and gas. Poor conductor of heat, poor conductor of electricity. Solids are brittle, they easily break. Gain electrons in reactions to become anions. They are in the upper right hand section of the periodic table except hydrogen. So you have some example here. You see bromine. Bromine is a liquid. Chlorine is a gas. Then sulfur is a solid. Let's look at metalloids. Metalloids show some properties of metals and some of non-metals, known as semiconductors. Properties: shiny as metals, conduct electricity as metal, brittle as non-metals. We want to look at other important divisions of the elements in the periodic table. Other important divisions of elements in the periodic table. Elements can be divided into columns and rows. Elements with similar chemical and physical properties are in the columns, or we call them groups. Columns are called groups, designated by a number and a letter at the top. Rows are called periods. So groups, main group elements, we call them the A group, include metals, non-metals, and metalloids. B group elements are all metals, transition elements. We call them transition elements, but they're all metals. Bottom row, inner transition elements, we call them the rare earth elements. Metals really belong to period 6 and 7. So we are going to take a look at the periodic table. So you see, this is group 1A, group 2A, group 3A, 4A, 5A, 6A, 7A, 8A. Then these are the big groups, you see them. Metals on the left, non-metals on the right. In between you have the metalloids. So some groups have names. These are alkali metals, group 1A. Group 1A elements, we call them alkali metals. This is 2A. We call them alkaline earth metals. These are transition metals. Transition metals. B group. These are noble gases. Noble gases. Noble gases. This is 8A. We have the halogens. These are halogens. Then these are lanthanides. And these are actinides. Alkali metals. Group 1A members. We have lithium, sodium, potassium, rubidium, cesium, and francium. Hydrogen usually placed here, though it is a non-metal because it has only one proton. But hydrogen is a non-metal. Group 1A metals are soft. They have low melting points and low density. Very reactive. Tend to form water-soluble compounds. All the compounds, most of the compounds for group 1 are water-soluble. React with water to form basic, or we call it alkaline solutions. So you see the formula: sodium will react with water to form sodium hydroxide and release hydrogen. This is a gas. Rubidium will do the same. Let's look at group 2A metals. Alkaline earth metals. We have beryllium, magnesium, calcium, strontium, barium, and radium. Harder, higher melting points, denser than alkali metals. Magnesium alloy used as structural materials. Reactive but less than the corresponding alkali metal. They are not as reactive like alkali metals. They form stable insoluble oxides. React with water to form hydrogen, not as reactive as alkali metals. So beryllium will not react with water. Magnesium will react with steam. Calcium, strontium, barium will react with cold water. Now you see the formula? They form the hydroxides. Let's look at the halogens. Halogens are group 7A elements. We have fluorine, chlorine, bromine, and iodine. They are non-metals. All diatomic elements, you see, that's how they exist. Fluorine and chlorine are gases. Bromine is a liquid. Iodine is a solid. Very reactive. React with metals to form ionic compounds. So, you see, X, they have acids. They form acids. All of them have acids. See, this is, they form acids, HX acids. HF is a weak acid. Weaker than ACl. ACl is weaker than HBr. HI is the strongest acid. The next group that I want to look at is group A, the noble gases. We have helium, neon, argon, krypton, xenon, and radon. All gases at room temperature. Very low melting and boiling points. Very unreactive, practically inert. That is why they are called inert gases or noble gases. Very hard to remove electrons from or give an electron to. So we want to look at ion charge and periodic table. The charge on an ion can often be determined from an element's position on the periodic table. Metals always form positively charged ions, e.g. cations. For main group metals, the charge is equal to its group number. For example, group 1, elements have +1 charge. Group 2, elements have +2 charge. And group 3 have +3 charge. So nonmetals form negatively charged ions, e.g. anions, and the charge on the nonmetal is group number -8. For example, fluorine or group 7 elements. 7 equals to 8. 7 minus 8. 7 minus 8. So their charge is usually -1. So we can be able to predict the charge on an ion based on its position in the periodic table. So we can see, look at the group 1 or the group 1A, we have +1, group 2 +2, group 7 -1, group 6 or -2, and group 5 -3. You see aluminum here. So please, the group number for metals give you the charge, which is positive, and for non-metal to get the charge is the group number -8. So please try and do this. What is the charge on each of the following ions? Potassium is in group what? Group 1. Okay. So it's going to have a charge of +1. Sulfide, which is from sulfur. Sulfur is in which group? Group 6. So the charge on sulfur, and sulfur is a non-metal. So 6 minus 8 is -2. So calcium is in which group? Okay, calcium is in group 2. So calcium is a metal, so it will form a cation. It will give up 2 electrons, so its charge will be +2. Bromide from bromine, of course, it's a non-metal and it's in group 7. So 7 minus 8 is -1. And aluminum is in group 3, is a cation. It will give up 3 electrons, so its charge is +3. So that is how you can use the periodic table to determine the charge on an ion based on the group in which the atom that forms the ion belongs. So counting particles in chemistry. Now we want to see how we can count particles in chemistry. For example, let's try and think about it. A dozen means 12. So when we talk about a dozen of cars, we mean 12 cars. A dozen of boys, we mean 12 boys. So in chemistry, we use the term mole. A mole is a number. A mole is a number. And that number is 6.022 times 10 to the 23. Just like a dozen is 12, a mole is a number, and that number is 6.022 times 10 to the 23. So when I talk about 1 mole of cars, I'm simply saying that I have 6.022 times 10 to the 23 cars. And when I talk about 1 mole of atoms, I'm simply saying that I have 6.022 times 10 to the 23 atoms. Or 1 mole of electrons is 6.022 times 10 to the 23 electrons. Because a mole is a number. So the mole concept. The value of 1 mole equals to the number of atoms in exactly 12 grams of carbon-12 isotope. So the number of atoms in 12 grams of carbon-12 is 6.022 times 10 to the 23 atoms. So another word for this mole is what we call Avogadro's number. As we said, a mole is a number. So another name for it is Avogadro's number. So if we ask, calculate the number of atoms in 2.45 mole of copper. We want the number of atoms. We know that 1 mole of copper is 6.022 times 10 to the 23 copper atoms. So we need conversion factors. Conversion factors. We are going to have 2 of them. 1 mole of copper all over 6.022 times 10 to the 23 copper atoms, or 6.022 times 10 to the 23 copper atoms over 1 mole of copper. So to calculate the number of atoms of copper, I need one of these conversion factors. So I'll take this one. So it's 2.45 moles of copper times 6.022 times 10 to the 23 copper atoms all over 1 mole of copper. So you cancel mole of copper. So this is just equals to 2.45 times 6.022 2.45 times 6.022 times 10 to the 23. So this will give us 1.48 times 10 to the 24 copper atoms. So that is what we are going to expect. So you need conversion factors, which will come from this relationship. Okay. So mole of copper equals to 2.45 moles. Copper atoms, that's what we want. So we have to move from moles of copper 2 atoms of copper. We need conversion factors. So 1 mole of copper is 6.022 times 10 to the 23 atoms of copper. So the conversion factors, we have this one or this one. So we are going to use this one. We'll use this one. So that's our answer. Let's take another example. A silver ring contains 1.1 times 10 to the 22 silver atoms. How many moles of silver are in the ring? So atoms of silver, this is 1.1 times 10 to 20 atoms of silver. Moles of silver, we don't know. We want to move from atoms to moles. And we know that 1 mole of silver contains 6.022 times 10 to the 23 atoms of silver. So we have 2 conversion factors. But we want to convert from number of atoms to moles. So this time we're going to use this one. So we put our number of atoms of silver, and we use this multiply by this conversion factor, cancel atoms of silver. So our moles of silver is 1.8 times 10 to the minus 2 moles of silver. So you want to try this? How many copper atoms are in copper wire that weighs 3.10 grams? Sorry, I'm reading something else. Let's look at this. It takes 2433.4 moles of aluminum to make a pop can. How many atoms of aluminum? How many atoms of aluminum atom are needed to make 2 pop cans? So let's try and do this. It takes 2433.4 moles of aluminum to make a pop can. So 1 pop can equals to 2433.4 moles. That is what we have. But we know that he said it takes 2433.4 moles of aluminum to make a pop can. How many atoms of aluminum are needed to make 2 pop cans? So 1 pop cans, we need 2433.4 moles. But we know that 1 mole of aluminum equals to 6.022 times 10 to the 23 aluminum atoms. So we are going to move from pop cans to atoms. So we are going to move from pop cans to moles to atoms. So that's what we want to do. And we need conversion factors in all this. So we'll start with 2 pop cans. Times, we want to convert to moles. 2433.4 moles of aluminum all over 1 popcorn. Then times, now we have 6.022 times 10 to the 23 aluminum atoms all over 1 mole of aluminum. So let's do our popcorns cancel, moles cancel. So when we multiply everything here, divide it by everything below, we are going to get the number of atoms of aluminum. So let's try and do that. So 2 times 2, 4, 3, 3.4 times 6.022 times 10 to the 23 equals to, so we have, let's just write this, 2930 7.9 times 10 to 23 aluminum atoms. So this is 2.93 times 10 to the 27 aluminum atoms. So that is what we're supposed to have. So we got that. That's what you're supposed to get. So let's look at another example. Let's see what we have here. How many copper atoms are in copper wire weighing 3.10 grams? So let's try and do that. Mass of copper, the 1 atoms of copper. So we are going to move from grams to atoms. So we have to convert grams to moles to atoms. So these are the conversion factor. This is from the periodic table. Sorry. So come up with conversion factors to use for this. So those are the conversion factors. So now when we put everything together, our answer is 2.94 times 10 to the 22 atoms of copper. So you want to try and do this on your own, so practice. How many aluminum atoms are in an aluminum can weighing 16.2 grams? So please try and practice with this one. So we have come to the end of chapter 2. So please make sure you do practice. Go to the back of your textbook. Practice the problems there. Of the problems in chapter 2, the odd number questions have answers. So make sure you check it and try to do even the ones that don't have answers just to practice. So thank you very much.